Okay, hi everyone. Can you hear us well? Is it fine? Okay, perfect. So, welcome to our presentation with title Data Warehousing Reinvented for Today's Needs. My name is Dimitrios Papageorgiou. I'm a Senior Solutions Architect for Amazon Web Service for the last 2 years. And together with Konstantina.
Hello, I am Konstantina Mavrodimitraki. I'm also working for AWS for the last 1 year and a half. Prior to that, I was working as a data engineer for ETL solutions from data warehouses to big data platforms. So welcome to our session today.
So, a couple of questions before we start. How many of you have worked with cloud services? Just raise your hands. And how many of you have worked with Amazon Web Services? Okay. And last one, how many of you do you have experience with serverless technologies? Okay, okay. So let's move to the next slide. Let's have a quick look at the agenda first. First of all, we will discuss about how and why the data are being exploited the last years and why it's a problem for the traditional data warehouses to handle them. And then we will discuss how data warehouses have been involved in order to address this increasing amount of data. Then we will show how the Lakehouse architecture comes to the picture in order to solve the problem that we mentioned before. And then we will put all the different bits and pieces together in order to present an architecture which tries to address that issue. And finally, we will have a demo. It's pretty short, actually, just to be on the safe side, in order to see a bit how all these things work together. So let's see, first of all, why we have an unprecedented data growth the last year. These are two reasons. The first one is that we have more and more connected devices. Before that, usually we had the application that the companies were had, the internal applications, the systems, the CRM perhaps, an ERP, and all of them were generating classic data, most of them being stored in relational databases. Nowadays, we have a lot of connected devices, we have cell phones, social media connected, streaming information, we have IoT devices, industrial, all of those devices generating different types of data. And by the estimations and calculations that have been made, usually the data nowadays grows like 10 times every 5 years, so it's really exponential, the growth. The second reason that we have an unprecedented data growth, it's the microservice pattern. We saw before the presentation also by Sebastian. And the thing is that nowadays organizations move away from the monolith platform, have like a large application taking care of everything, and they break their complex problem in different solutions. Teams can work independently on their different services and features, and they can work really fast to accelerate their implementation journey. But this has two caveats. The first one is that the different microservices, different technologies, different programming languages, different types of communication generate different types of data. And also that the communication is way more complicated, more services, so we need to have better observability, monitoring, and logging in order to figure out what's wrong with our system. So the data warehouse that we're until now facing three problems. They have really problem working for the volume of data that have been generated, the variety of data, since we might have JSON, the CSVs, tabular data, whatever you name it, and also the velocity of data. As we saw, we have a lot of streaming use cases by social media, by logging, monitoring, and generate increasing amount of data. Actually, I had a discussion with a customer 2 days ago, and they were mentioning that they try to do monitoring log, and they have like 1 terabyte every 24 hours, which is like a huge amount of data. Therefore, the data warehouses have to be evolved in order to address this problem. When we say modern data warehouse, it has the following characteristics. First of all, it has to address the data flexibility. As we saw, relational data, CSV, JSON, streaming, everything has to be taken care of by a modern data warehouse. They have to be simple to use and also scale, because we don't want to invest time like setting up the cluster, patching the cluster, monitoring what's happening. We need to focus on what makes sense for our organization. So therefore, if we could focus only on working on the data warehouse and it can scale automatically up and down, then it's a really important characteristic of the modern data warehouses. Other important characteristics also we need to pay for the resources that we are using. It doesn't make any sense nowadays to provision a large cluster and having like 10 gigabytes of data. It makes sense to use only the resources that we need and also pay for the resources that we need. And also, what is very important here is that we need to pay also for the resources that we're utilizing. So if we are needing 10 gigabytes of data, 100 gigabytes of data, 100 terabytes of data, we need to pay only for this infrastructure. And also, they have to be, we're living in an AI world, of course. Everyone is talking about generative AI, machine learning, AI. So modern data warehouses have to address that because use the data in order to get useful insights from them. A very good example of modern data warehouse is Amazon Redshift, which is a petabyte scale data warehouse service born and raised in the cloud. It offers 3 benefits. The first one, it's able to analyze the data no matter from where it's coming from. If it's from a relational database, if it's from a third-party provider, if it's like from a data lake, Amazon Redshift is able to handle those, combine them, and generate insights from them. The second one, it offers very good price performance even at scale. We have a lot of opportunities on how to scale our infrastructure, either horizontally by adding more cluster, by updating the instances on the fly if we need to get more compute power, or utilizing features like massive parallel processing, query caching in order to address use cases where we have spikes in terms of compute. And finally, it utilizes the AWS infrastructure, so it's easy, secure, and reliable, since all the downstairs and differentiated heavy lifting, let's say, it's being taken care of by Amazon Web Services. Let's see now a bit complicated slide. Here is how the architecture of a Redshift cluster looks like. It consists of 2 types of nodes. We have the leader node, which is our interface. The SQL clients are connecting there, the BI tools are connecting there, and it's responsible of taking the query, analyzing it, compiling, and distributing to the different compute nodes. The compute nodes is where all the magic, let's say, happens. They are responsible for different chunks of data. So they have a share nothing architecture, so they can really utilize more and more in order to query them in parallel. And this means that we really get very good performance. It's really important if we're working with petabyte scales. And we have to query very large tables or facts. We need to get this information as fast as possible. This get the data, they get the query, get the data but needs, send it back to the leader node, and then does the aggregation in order to get them on our interface application that we are using. If we want to scale a bit more and add more and more data storing there, we could utilize Amazon S3. S3 like it's an object storage where we could store a lot of data with a very good price. And by doing that, we could utilize the different feature of Redshift in order to get the information that we want as fast as possible. And if you want to see now how the big picture looks like if we go one step higher, actually we have in the middle our data warehouse, where we have our most important data, we're doing the query there, so we need some compute, and this is in the heart of our system. If we want to add more data, but we don't want to query them as fast as possible, or they don't make any sense to pay for the storage for the data warehouse, we could move them one step lower, store it there, and utilize the different Redshift features to query them. If we want to get data from our relational databases, we could get them directly from federated queries. If we want to get data from third-party providers to get some useful insights, trends, and so on, we could also utilize the data sharing. And finally, we could utilize our machine learning functionalities from Redshift in order to get the insights from our data. We'll see later on in our demo how we could try to predict some orders from an imaginary company.
Okay, so we discussed about Redshift, the data warehouse solution that we have. Let's take a step back now. Dimitris already discussed about S3, our object storage service. So in order to put it into the picture, let's take a step back and introduce 2 terms, hot data and cold data. So by the term hot data, we mean data that is frequently queried. It's vital for our decision making. And we really need them for the present decision making. Cold data is data that is considered old. It's more than a year, maybe, data. And mostly we store them for audit and backup purposes. So, as you can imagine, hot data will be stored in Redshift, and cold data will be stored in S3 in order to leverage its cheap storage tiers. In this solution that we're discussing today, we will use S3 for 3 main purposes. The first is that it will act as a landing zone for our data, and this is because we want to, let's say, leverage its rich ecosystem of connectors. So we land our data into S3. The second, we would say, purpose for using that is to store, as mentioned, our historical data. But of course, we can combine them with our hot data, which lives in our data warehouse. And this can be done seamlessly from the data warehouse. We will see that in our demo that follows. The third reason why we will use S3 is because nowadays, as already explained, we have structured and, of course, unstructured data, semi-structured data, logs, CSV files, JSON files, images, videos, etc. All these can be stored in S3. We can then do the transformations needed, and we will load the structured, let's say, result in the data warehouse. So in order to store our data in the data warehouse, we need to do ETL. So we need to transform the data, cleanse the data, combine. So there are a number of options here. Traditionally, this is done inside the data warehouse. This is what we call ELT, extract, load, and transform. Then we have ETL, which basically you extract the data, you transform it, and then you load it in the data warehouse. And of course, you can have hybrid approaches. So with AWS Glue, which is our integration service, we are doing ETL. So we extract the data from the service, from the S3 service, where it's stored in place. We transform it, and we load it in Redshift. And why we will use AWS Glue? Mostly for platform independence, basically. On top of that, it's also a serverless service. This means that we do not have to handle any capacity. In addition to that, it's a pay-as-you-go pricing model. That means that when your jobs stop running, then you stop paying basically for that compute. It's also scalable. Data grows. AWS Glue will grow. Will scale actually to accommodate that growth of data. One final thing is that it can, let's say, adjust to the diverse skill set of your teams nowadays. We have data analysts, data warehouse engineers, data engineers, different skill sets. It can accommodate, as we will see, all these different skill sets. So let's see some of the key capabilities. We have a number of integration engines, from plain Python to the very popular Spark framework. Basically, your teams can use either Python or Scala to create their jobs. A number of Glue connectors, from native options to connectors that are that you can find in the marketplace, that our partners have developed, and of course you can build your own connector. So, as I mentioned, on the authoring options, we have visual interface, AWS Glue Studio, which we will see today. So it's a basically no-code interface that allows your data analysts to really quickly prepare jobs and, of course, schedule it to run as well. But we also have options for your data engineers, your data practitioners. They can write their code either Python or Scala in the Glue notebooks. Now, one of the most, I would say, prevalent features of Glue is AWS Glue Data Catalog, which is our central metadata repository. Basically, this allows you to catalog your data independent of where they reside. They might be in S3, the storage service. They might be in Redshift, the data warehouse. They might live in relational databases on-prem, on AWS, on other cloud providers. But you catalog them, you create metadata for this data, basically in one central location. And this actually allows you to discover and analyze this data without actual data movement. And we will see that also in our demo. One final thing here is that there are also some features on data quality. So we have some rules that you can use. You can also build your own rules in order, let's say, to control the quality of the data that enters your data warehouse, which is really important, one of the most important parts, I would say. Finally, we have Amazon QuickSight, which is a scalable ML-powered BI service. It has been basically built for the cloud. It's, again, serverless. You don't have to provision any capacity. It can scale also from tens of users to thousands of users seamlessly. You don't pay any license. You just pay when your users access the dashboards. You get all the classic, I would say, features that you would get in a BI tool. And on top of that, you can get some ML-powered insights, like building anomaly detection and forecasting. You can also get written narratives to interpret your data for you. And now with Gen AI, all the latest developments, we also have Amazon Q, which basically allows you to write natural language, so without any SQL, write your queries and get your results of your data. So let's put it all together, demo time, more interesting stuff. So in this demo today, we have Any Company. Any Company is an e-commerce company that operates in the US market. They serve their customers across the US states. They deliver thousands and millions of orders every month. So they plan to build their data warehouse in the AWS cloud. And basically, they want to build their dashboards in QuickSight. They want to basically enhance the experience for their users, understand the products better, and deliver better user quality and experience. In addition to that, they want also to build a machine learning model in order to predict the upcoming number of orders and, let's say, manage their inventory more efficiently. And in general, all these requirements need to be built here in AWS.
Built with AWS services, just to depict a bit what we discussed and what we're looking here. So we said we need to have like our landing zone of data and our data lake, where we'll keep putting all the information here. So this is Amazon S3, which is the object storage. We said that we really want to build our ETL jobs, the data catalog, which has the information of the schema of the data. So we'll utilize Glue here. Then we will have our data warehouse, the actual data warehouse service, which is Redshift. And we will use different features also to query our historical data. So we're combining the data lake with the data warehouse. And we use the Redshift ML to get some insights from the data by using machine learning models. And finally, we will have the visualization with some nice dashboards to keep our CFO happy.
Okay, let's start with our demo. So the first part, we will catalog the data in place in S3, and then we will create a job with AWS Glue Studio in order to load our data, transform our data, denormalize the data basically, and load it in Redshift. Let's see. Okay, so this is the AWS console. As you can see, you can also get a visual of your recently visited services, so accommodate that. So let's navigate to S3. So this is where we can see these are the buckets. These are basically, buckets is what we call basically the folders, let's say. So let's see, here, this is our landing zone. This is where our data lands, and we can, basically from there, we can catalog them, and basically from our job, we will find them and combine them in order to load them to the data warehouse. So we have orders, order items, and products. These three data sets will be joined in order to load them to the data warehouse. But as mentioned previously, S3 will be also the place where we will store our historical data. And we will see in the next video, basically, how we will combine the data that lives inside the data warehouse with the historical data here, historical orders and historical order items, in order to have a seamless, let's say, experience for the user of the data warehouse. So now the first step is to catalog our data in order to be able to use them and create our transformations. And for that reason, we will create first a database. And this is where basically our metadata will live. So let's give a proper name. Now that the database is ready, we will create our first crawler. Crawler is what we call, is the feature that we call that basically will crawl the data and bring the metadata in. So we will create one crawler. Again, a proper name. It's always good to have a naming convention strategy in place. What happened? Okay. There seemed to be, I saw it also with the previous presentation at some point. Okay, let's continue.
It's good to have the demo recorded sometimes.
Yes, but again, you even have problems with the recording these days. Anyway, so again, we create the database. And let's create now the crawler. Okay. So the first step, basically we will point to the crawler where our data lives. Here we have a number of options, as we will see in the next step here. For us, the data resides for the particular demo in S3, but as you can see here, there are other options like JDBC or Dynamo, which is our NoSQL database, and MongoDB, so there are a number of options, of course. So here, why is it losing? Okay. So here we will point basically to to where the data lives inside the S3 bucket. Here we need to give a proper IAM role. This means that we need the proper permissions in order to access the data in S3. So we need a proper role with these permissions in place. And then at the final step, we set the output in the database that we just created. And we can give also some prefixes, again, which should be in line with our naming convention strategy. We are ready to review, and we create our crawler. So now we run the crawler, and in a few seconds we will see the result of the crawler in the database that we just created in the first step. So we can see here also that there is a table change, so it detected, of course, a table. In the crawler, of course, you can add additional sources, so it's not just one-to-one, let's say, mapping. So here you can have, we can see basically the column names and the data types, and this is version 0 of the schema. Of course, we can edit the schema, as we can see now, and add proper names. We can change also the data types, so we can do a number of things. We will save it, and we will see now that a second version, version 1, basically, will be created. This allows us to keep the schema evolution. As the schema changes on our data, we can see also here that we keep the versions there in order to use them if needed. But in general, we can use it in order to follow, let's say, the schema evolution, which happens in our transactional databases. So now we will create our first job. So as I mentioned, we will use AWS Glue Studio, which is a visual interface. You are allowed here basically to give a source and a target in order, let's say, to accelerate the creation of the job. From here, for us, we have chosen as source S3 bucket, and we will offload the data after we transform it into Redshift. So as we will see, there are a number of transformation sources available and things that and outputs that we can add in our job. So the first thing that we need to do is give a proper name again. And then, as you will see, from the S3 bucket, we have a visibility to the data catalog, which is the data that we basically cataloged. So we will choose, as you will see, the appropriate data catalog table. We will give a proper name. It's always useful in case of debugging. We will choose the database, and we have visibility basically on our data. Really easy, I would say. So the first data set is there. Let's add one more source. Again, from S3, from the data catalog. As you can see, basically the data can live in different locations, but through the data catalog, as I said, it's a central metadata repository. Seamlessly, you can find it and add it here. So it's really convenient, I would say. So here we have the order items. And let's bring our first transformation. We will bring basically a join the two data sets. Now, we will change the node parents once we have a proper name, and we will add orders and order items. Basically, this allows us to play with the, to change, let's say, the visual, as you will see. So, we have a number of options for the joins. Here we will choose an inner join, which is a good practice for data warehouse. And we will put, of course, the join condition. Now, we will put one more source in order to further denormalize our data. This is the purpose of a data warehouse. You need to denormalize the data and avoid, let's say, as much joins as needed on the final, when you're querying basically the data. So we will put one more bucket here. We will bring the products. It's already cataloged, so things are easy. And we will bring one more join transformation, which will basically have as node parents, as inputs, let's say, the product of the first join and the new data source. And of course, again, we will put the join condition. So our data is almost there, it's almost ready. We need a final touch, a final transformation, and we will load the data into Redshift, as you will see. So we click on the final step and we add one more transformation. So at this step, basically, we are doing some last, let's say, changes, final touches on the schema. We can drop columns, we can change data types, and finally, when we're ready, we're loading this data to Redshift. As we will see, we will change the node parent of Redshift to basically point to the change schema so that we load the final part. The tables in Redshift have also been cataloged, as I told you, so it's a central metadata repository, so we can also, from the data catalog, see the tables that reside in Redshift. So again, it's pretty easy. We can see the database where the Redshift table exists and choose the particular table. And then we have a number of options on what to do with the data inside the Redshift. We can append. In the particular case, we will truncate and insert. So it's more of a staging table, let's say, load the data in, and then do more things, let's say, append inside the data warehouse. So here, final touch, before saving, we need to put on the properties tab an IAM role that will have basically access to S3 and Redshift. This is needed. We can see the version of Glue, the Python version, and the number of workers. Further down, you can see that there are 10 workers. That means that the data is being parallelized between 10 different nodes in order to accelerate the transformation. We can also check there the logs, basically, of the Spark UI. So let's save and run the job that we just created. And we can go actually now to the Runs tab in order to see further information on our job, like when it started, when it ended, the duration, the logs, information on the version of Glue, again. So it took pretty 10 minutes in order to load 22 million of data. So let's see now the data inside the Redshift.
Okay, what we saw until now, we store the information on our data lake, and we build the ETL jobs which will bring the data to our data warehouse. I remember the quote from Voxxed Days. It's called from developers to developers. We haven't developed any code, but we will keep it like that. Of course, you could also build like this with infrastructure as code, like Terraform, Pulumi, CDK, you name it. So let's move now to the data warehouse part, in order to see how the data looks like there. Here is the console of Redshift. We're utilizing the serverless version of it. And by saying serverless, we don't have clusters, we don't have nodes, we don't have CPUs, we don't care about these things. The underlying infrastructure handles this. We only setting up, as we will see later on, the RPUs, the Redshift processing units, and according to the needs, they're going up and down on demand in order to address our needs. So this dashboard is consisted of different widgets. One of those, it's the namespace widget, as we're going to see later on, and it's one of the most important ones of this dashboard, this console, because it has information about our databases. Schema, database, tables, all this information is being stored on this widget. And it also has some additional information about the backups and also about third-party data if we are integrating with a third-party provider. In this demo, we haven't didn't have time to implement also this case. Also some information about say, encryption keys, usernames and passwords, and then a link to another dashboard, which is called a workspace. The workspace has the actual compute information. As we mentioned, we don't have CPUs here, but we have the RPUs. We could set up some limits until 10, 12, 16, whatever, in order to keep our costs in a, not explode without understanding why. And also some information about our network infrastructure. Although it's a serverless service, we need to have it in our virtual private network in order to secure it from external access. Other widgets that we have here, we have information about our queries, what types of queries have we run, how many are they successful, how long it took them to execute, so it gives some information for monitoring purposes. And also very important, it's our RPU graph here, which we can use it in order to see how many RPUs we have consumed and how many time, in order to help us have an overview about the costs that we're going to spend in our infrastructure. It's the pay-as-you-go model that we mentioned before. We need compute, we get more RPUs. We don't compute, RPUs goes down automatically, all these things. And some other information, we could have the free tier version for our warehouse service, and also some alarms in case that it's not working properly in order to get alerted. Now we saw a little bit how we administer our console. Let's see now how our data looks like. Of course, we could connect any SQL client that we have, like dbeaver, everything, but we're going to use the query editor, which is part of AWS console. It's also a web interface. So we're going to change color a little bit here. We're going to go dark to keep away the bugs. So let's see how the console looks like. On the left part, we have the tree view, classic tree view for SQL clients, schemas, databases, tables, attributes, classic stuff. On the right part, we have our query editor. And let's try to query the tables that were generated by our ETL jobs. As we can see here, we have the orders, order items, customer, categories. All these things have been moved successfully to our data warehouse. So we can use them to query them, join, views, trigger. It's based, actually, Redshift is based on the Postgres engine. So we have a lot of similarities in terms of writing SQL code there. So since any company is a retail shop, they really need to understand how many orders are they going to receive in the future in order to have the appropriate inventory and support their customers. So in order to do that, they really need to build a machine learning model which will read all this data that they have already and try to predict, let's say, in the forthcoming months, how many orders are they going to get in order to be ready for those type of orders. So in order to do that, they don't have a very large engineering team. They don't have AI engineers, machine learning engineers, and so on, Python engineers. They're really focusing on their other programming languages, so they try to build all this machine learning functionality only with SQL commands. So by utilizing this feature of machine learning, Redshift ML, okay, they're going to get the useful information that they want from their data. So we just try to build a simple model which has information about the amount of orders, which day this order took place, and if it was a holiday. It's just a simple parameter to our model in order to have an overview about how people operate during holidays or during normal days. We have like the model we ran before in order to save some time because it takes more than an hour. And here we have the information, which is not very visible here, but the study of the model is ready. And by meaning ready, we could utilize this model, and we will try to see what values are we getting in order to see if we had a good result. So here we're calculating the inference, comparing the values that we get with the actual values of past orders, and here we get the difference in order to see if it makes sense to keep working with that model. So in that case, although it was simple, we get good information. So we will keep that, and we'll keep working that in our dashboard case in order to see how it will look like in the distant months and what type of items should we order in order to get the information that we want. Also here some AI stuff, most probably, because they translate my language. I just saw it. Okay. So another part that we need to utilize in our infrastructure is to get the historical data. As we saw before in the beginning, we keep our historical data in our data lake. We will try now to connect to this data without moving them to our data warehouse, because it doesn't make any sense to keep them there, since the cost will get higher without any particular reason. So here we go to our data lake, and we see this data, the historical information, which were a couple of years ago, and we will try to query them in order to get if it makes sense to join them with the existing information that we have. In order to have access to this data, we will use once again the glue crawlers, as we saw before. We built again crawlers to crawl to our data, get the information, and build a schema in order to know what type of information I have here and be able to query them directly from the data warehouse. So here's the crawler part. We run them already, and from the database, as you can see, we have this spec_spectrum database, which has the information about these two tables. So let's try to connect to this information. We utilize the Redshift spectrum, which is a feature about connecting to our data lake. We will build a new schema, which, let's say, it's a virtual one. We're not moving our data to our data warehouse, and we'll get also these virtual tables. As we can see here, we have it already. They're not being stored in the data warehouse, a depiction actually of what we have in our data lake. Let's try to query them to see if we have successfully done this movement here, and as we can see, we get this information. We could really build a join on them, and we could also combine them with the existing data in order to get reports that are not very common, let's say, or used like once a month or so. So we build this feature that the company wanted, and let's go move and how they will look like in the data visualization part.
Okay. So last part. We have our data in place. It's denormalized. The dimensional model is there. Let's build a proper dashboard. So on the left, you can see there the data set. So we need to add a data set in order to build afterwards an analysis and a dashboard on that. Here we have the query that will load our data from Redshift. I have already done the appropriate part of connecting, let's say, to Redshift. We can build hierarchies. Here we have a geo hierarchy, as you can see. And we will see that also in the dashboard. And we can also create transformations in QuickSight. We can leverage the functions that QuickSight is giving us. And we have also dataset parameters that allow us to control, let's say, the data that we see in our dashboard, in an analysis. So let's create an analysis. So I have already created an analysis with the proper controls that basically control the conditions that we created in our dataset. We have a number of options for the visual types. As you can see, here there's a KPI, key performance indicator, and we can, as you can see, we can change the date and see basically that the visual changes. Here we have a combo chart, and it allows us again to drill down in the time hierarchy if needed. And also on the right, we have top performers for products and bottom performers for products, a really quick thing to do if needed. Heat map, and again here we can drill down, zoom in, let's say, to the state, or from the state to the city, and further down to the zip code. Of course, we can zoom up again. And here we have a map where we can see the distribution of sales across the US states. So really quick, let's say, way to check our results. When we're ready, we will publish the analysis into a dashboard. That means that we have a read-only version of this analysis. And this is the dashboard. We can, again, of course, have the controls, the prompt controls, in order to control our data. And on top of that, we can also create alerts. So if needed, for example, if a condition is breached, we can also inform particular people in order to act and remediate if needed. Final thing, I mentioned again, Gen AI is is a thing that we hear a lot these days. So here with natural language, basically what you can do is that you can write your queries. So users that don't have knowledge of SQL, they can write their queries in natural language and get the results. Of course, they can edit also these results. These are, let's say, the standard visual types, but of course you can add more. We can see here, for example, that with natural language we can have this type of feature. So this concludes our demo today.
So thank you very much. See what we built. Please give us some feedback here. So scanning to get some information. And if you have any questions, we are here. I'm not sure if it's a lunch break or...
There is a lunch break, but any questions? I mean, we do have time for 1 or 2 questions. Anyone? Just lift your hand and stand up and talk loud enough so we can hear you. I think we have a question over there. There you go.
So I was wondering, can we interfere in any part of this with codes?
Yes. The short answer is yes. Now we build them always click by click. So it was a simple case, so the ETL job find the schema, generate quickly the data tables. It might be you need to do some combination or whatever. You could really go with Python code, write your script there, and do whatever transformation you want.
Sorry, Dimitri, something that I didn't mention before, that first on the Glue Studio that we created, basically you can see you have access to the script that it creates under the hood. So how you can use it is that really quickly do a few, add the sources, the targets, do some simple transformation, and then switch to the script, let's say, and add additional code there. It's plain Python. Spark framework, you can edit it. But if you don't want to deal with it at all, then you can write your code in a Glue notebook. Plain Python again. There are some extensions that AWS has, some libraries basically, in order to further, let's say, enhance the Spark framework. And of course, then you can continue you can do your main transformations, I would say, with Glue. In place, you can have a data, like let's say in S3, different data zones with landed data, raw data, cleansed data, and then load, let's say, the data for further, maybe more closer to the user transformations inside Redshift with stored procedures, for example.
Actually, if you want to try it, come find us. We'll give you a code for some AWS credits to turn into your account.
There you go. Awesome. So thank you both. We have an hour's lunch break. Don't forget to connect and network with everybody, and we'll see you back here in an hour. Thank you, guys.
Thank you.